All right, we're going to take a look now at our final lesson video for Unit 1A, Lesson 9. We're going to be talking about segment and angle relationship proofs. And these are going to be more of what we consider non-algebra proofs. So we're going to talk about the differences between the proofs we've already done so far, which have been algebra proofs, meaning we've been using equations. We've been using our algebra properties, algebra skills to solve these equations and do that in proof form. Well, non-algebra is a way we're going to prove certain ideas and facts based on the geometric definitions or properties or postulates or theorems. And so there's some differences and similarities we want to look at. Okay, first we'll look at some similarities. Okay, we are still proving a statement based on the given information. We're still starting with our given and then following that up with the next series of logical steps. Okay, we're also still going to use reasons. Okay, and these reasons can be postulates. A new word we're going to look at later on is called theorems, like the Pythagorean theorem, or properties, or definitions. Okay, my handwriting is getting a little rough there, but you can write those down. So we're still going to follow those same kind of steps, but here are some key differences. Some of our main differences include that we're going to rarely use substitution. We're not using algebraic equations, so we won't really be doing the part plus part equals whole here and substituting in values using x, okay? So we will still use some substitution, we will still use some numbers, but we're not really using the algebra, we're not using equations with variables, okay? No EQS means no equations with variables, okay? And then we're gonna do more congruent statements than equals, all right? So we'll be using congruent examples rather than equals, and we'll talk about some of those differences as we go. Let's take a look at our first example if we turn the page. Okay, we're going to take a look at our first example here. I'll zoom in for us. And we are given, again, a similar situation to what we were given last time. We're using midpoint this time, but we are going to prove that segment AM is congruent to segment BN using definitions and postulates and ideas that we have talked about already. So again, the very first thing we want to do is write the given out. Okay, didn't leave myself a lot of room, but that reason is that it is given. Okay. And then we want to go from there and prove, eventually, that AM and BN are congruent. Now, to do this, it really helps if we draw a segment. So I'm going to draw this out, that M is the midpoint of AB, and B is the midpoint of MN. Now, we're going to assume these are collinear then, because of how this all works out. Okay, so there's A, and M is the midpoint of some segment AB. This is not B, okay? And I'll tell you why as we go through this. Okay, I'm going to put B right there. M is the midpoint. I'm actually going to back up a little bit. I'm going to move B. Sorry about that. We're going to move B right there. And I'm going to put M right there. So M is the midpoint of segment AB, but B is the midpoint of segment MN. Okay, so that means it's also congruent there. Now, as I've drawn it, you can see all three segments are congruent. Okay, if AM is the same as MB, because that's what midpoint means, and MB is the same as BN, because that's what this midpoint means, then AM has to be congruent to BN, but we're going to write that out as our proof. Okay, so what we're going to do is we're first going to explain the meaning of the word midpoint for this midpoint M. And that means that segment AM, that part, is congruent. Notice I'm using congruent because my proof is congruent, not equals, to MB by definition of a midpoint. That's what midpoint means, so that's my reason. But I can do the same thing for B, for this other part, all right? I can say that MB is congruent to BN, again, definition of midpoint. Well, all we have to do now is link these together because AM is congruent to MB and MB is congruent to BN. Remember, we have a property that allows me to chain those together like a train is the example I gave in class. And so I can just kind of fold that over onto itself and get rid of the middleman. I can say AM then is congruent to BN by the transitive property. And this is a property of congruence, so we write POC. And that's what we were trying to prove. Okay, so that proof is done. So this is a lot shorter method than having to work with a lot of equations. Okay, we're going to finish up with example 2. And before I even write my given down, I'm actually going to draw this. I'm just going to read through it and draw it because we could draw our picture before we start our proof, actually. We've got ABC as a right angle. So I'm going to draw angle ABC as a right angle. A, B, and C is a right angle. And we're told that BX bisects angle ABC. There's X, and it bisects it, cuts it into 2 equal pieces. Well, obviously, we know that each of these is half of the right angle, and a right angle is 90 degrees, so half of 90 is 45. That's what we're going to show in the proof, based on our definitions and other properties. Okay, so we're going to start with our given information that angle ABC is a right, RT period, angle, that's our symbols, and ray BX bisects angle ABC. And that is all given to me, so that's my reason. And now we're going to try and move on into saying what we're trying to say that it is 45 degrees. So I want to use the fact of what bisector means and what right angle means. Okay, right angle means that that's a 90-degree angle. So that's the first thing I want to say. I want to say the measure of angle ABC, so M angle ABC equals 90 degrees. And that's what a right angle means. So that's our definition of right angle. Okay? Because I want a statement kind of like this, that the measure of an angle equals 45. And we're going to use our definition of bisector to explain that 2 times the measure of XBC, this part, has to equal this whole thing. That's what definition of bisector means. So I'm going to say that. 2 times the measure of angle XBC, and I chose XBC instead of ABX because my proof uses angle XBC, my proof statement. So that's the one I chose for the part. Equals the measure of angle ABC, because that's definition of bisect. Okay? And the reason I'm doing this is to set up where I can substitute 90 in here now. And so I will use substitution here, even though this is a geometric proof. We're still using a little bit of equal signs and substitution. Okay? I can't substitute with congruence. If that was congruent, I wouldn't have any numbers. Okay? But it's an equal sign, so I can substitute in there, making this 2 times the measure of angle XBC equals 90. Again, we just substituted in for ABC. Well, now it's just about actually doing a little bit of algebra. We are going to solve this equation for the measure of angle XBC by dividing both sides by 2. So this is still considered a non-algebraic proof because we're not using a bunch of algebraic expressions like 4x minus 2. But we do divide both sides by 2 here and get the measure of angle XBC. 90 divided by 2 is 45. Okay? And that is just the division property of equality because I'm using an equal sign. And that finishes that proof. So we will use some algebra skills even though we're doing what we consider to be non-algebra proofs. Okay? That's going to wrap up our video for the notes. We will take a look at example 3 in class.